Hello, and welcome to Challenges to Scaling MySQL. How do you know you're hitting capacity? I'm David Selmy. I'm the Director of Product Management here at ClustrixDB. We provide a new SQL scale-out relational database for high-volume, low-latency transactions, high-value transactions. Today we're going to discuss different ways, and we're MySQL compliant, obviously. So ability to scale out your MySQL solution has a lot of challenges, as people have seen through multiple implementations for multiple years. And so today we're going to explore different ways of actually knowing when you're going to need a new solution, knowing when your solution is sufficient, knowing when all the different options you have for scaling out. Questions for today. What measures tell you when your MySQL deployment is hitting capacity? How far can you improve your MySQL capacity with hardware? How can architectural changes like sharding, read slaves, master-master replication expand your capacity? And what are the trade-offs that they have? And when is it time to replace MySQL with something else? So exploring a little bit about hitting capacity, we like to do that with a kind of a visual. Typically people, when they have a high-growth application using MySQL, are going to start with, obviously, the LAMP stack, Linux, Apache, MySQL, and either Perl, PHP, Python, or something that starts with D. You usually deploy this on AWS, Azure, Rackspace, Google Cloud Engine, or even in your own data center. What will happen is when you start getting more and more users, the users are going to notice that the application is too slow. Your system providers, your DevOps team notice that the systems are starting to get overloaded, the capacity limits are being reached. And what will happen is either the application users are finding the system actually isn't there, or they'll find out that it comes on too slow. Previously, Google did a lot of research and have said, hey, when your site is actually taking longer than a second or 2 seconds, people will leave. At this point in history, that's way too long. People, if they find it takes more than a second, they're going to absolutely leave. So the difference between a site that actually is unavailable, and you see that a lot, for example, in Cyber Monday, where very large companies that should know better every year seem to keep on hitting capacity limits and they have downtime. And so part of why that happens is not because they're dumb, is because they were trying to beat the capacity expectations from last year. But if this year they actually get more customers, it turns out your business success is your site failure. What will happen is you've created your capacity expectations for this year and you've resourced them, and maybe you've added 20%, and that's the most you can get out of finance, for example. And what will happen is that wasn't enough. The reason this happens is it's not trivial to be able to add capacity to a system that's relational and be able to remove it when you don't need it. So the finance people and, of course, your IT DevOps team will look and see, wow, I have this big capacity I have resourced for a very specific peak. For example, for the end of year, Cyber Monday, it's usually just before December through January. So 2 to 3 months, you have 80% of your entire yearly revenue. And yet, the rest of those months, your system, if it's provisioned for those 2 to 3 months, is sitting there idle. And that's really hard to take when you're looking at your budget just draining and the systems are not being used. So the challenge here is not just how do I get all the capacity I want, it's how do I get it and then remove it when I don't need. So for example, here, they've created a bigger box. The bigger box wasn't sufficient. So then they'll try to go to, for example, the bigger box, or they'll try to go to adding more capacity using different architectural tricks. One of the examples is read slaves, where you add a particular reader node, which ideally offloads all the read capacity to a separate node when the write capacity goes to your master. Or, for example, sharding, where you split the database itself into multiple different partitions, each on their own database. We're going to drill down into each of these specifics and give better examples of each and the pros and cons of each. But right now, just as an overview, this is also a lot what you'll see when you have a deployment on a large e-commerce site or a large high-volume transactional site, even internally, when you have a lot of people accessing the same kind of reports in your large enterprise. Or, for example, web scale needed in a startup when they start doing providing services that other people and tons of customers get and need, and as soon as part of your freemium model starts to pay off, you get a cascade of users start entering your system. How do you provide that ability to gain that scale without your system slowing down, which in turn, in this modern age, means your system's offline? One of the ways when they add read slaves, they add sharding, they can start to think of replatforming to actually leave MySQL completely. And so they try, for example, they go to a very large, very expensive relational data store, like a SQL Server, like an Oracle. But for many people, that's not an option. Or they'll say, well, hey, there's this new SQL that provides lots of scale, or NoSQL that provides lots of scale. That, for example, you can get it free. You can get a KVS, a key value store, from Cassandra. You can get a document data store from Mongo, and they're free. Why can't I deploy that? Tons and tons of nodes. The problem is now is you have to rediscover what's missing in a non-relational data store. That non-relational data store is not going to allow you to join data across different tables. It's not going to provide what we call ACID compliance, atomicity, consistency, isolation, and durability per transaction across all the nodes. And what that means is when you actually do a transaction, when your system says, oh, I want to update this, for example, in e-commerce, I want to have a purchase, and I say, is this available to promise actually match my inventory? If two different nodes are tracking the data, and you're going to want to do that to be able to get your scale, what will happen is that one node is not exactly in sync with the other node, and now you get to checkout, and now the checkout says you have something you actually don't have. This becomes a big customer problem for your brand, for example, in e-commerce, and you're going to have to revoke the transaction later. And at this point, there's a lot of feedback from the customers to the actual client companies, and what will happen is they post on social media. And so not only that person has left your site and is upset, and they might not ever come back. So you've lost the transaction. Now you've lost also the customer lifetime value. But if they post to social media, that's a force multiplier. Now a lot of people realize. And so if you look, we actually blog about that. You see Staples, Best Buy. Every year they get downtime. Every year they have problems in their transactions because for the same description I gave before of how do you predict the resource utilization you want without creating overcapacity and draining your bank account. This last step is, even though you've created all these different infrastructure that expands to be able to handle the capacity, what do you do when you hit the wall again? And so you kind of go in circles. You say, okay, well, maybe I should split the application to do two different sets of sharding infrastructures. And maybe I'll do the analytics over there. Maybe I'll do this system over here. And every time you add another system, you create another gap between systems, which provides all kinds of problems with latency, with consistency of data, and with the problems of the expectation that your data matches your actual inventory. Scaling relational databases, here's the different ways to do this and why, for example, it's very hard. Back in 2006, there was a famous article called SQL Databases Don't Scale. And what they described was pretty far came down on the issue. NoSQL allows you to scale with each new node, and each node is what we call completely shared nothing. So its memory, its CPU, and its storage are all specific to that node. That means each node I deploy can add additional linear capacity. And that works great with a NoSQL, which doesn't provide those ACID guarantees per transaction across all the nodes. To be able to do that relationally, and the reason we need relationally, which means structured data, is structured data maps very well with the business rules. That I have a lot of customers, we'll put them in a customer table. Well, I have a lot of invoices, put them in an invoice table. If people say, well, what's the need for that? If I have, for example, a key value store, I can say this customer has a record, and that customer record has all the information of their actual inventory, of the orders that they made, the order lines that they made, and the shipping fulfillment data, all that stuff in a row. And so then I can go, hey, here's this customer, and here's the order they had. And so if you think about it, if I've made multiple orders on Amazon, for example, then I'm going to have multiple rows there of me, the customer. But what happens if I change my name? What happens if I change my shipping address? I'd have to go do a cascade update across all those different rows. And that becomes a big burden in the system. And if you miss any one of those, you might ship to the wrong address next time. This is why relational data, where you want to say one data element stored once is your master. So I have a master customer record. If I need to change its address, or even multiple address types that are childs of that master record, I don't have to concern myself that if I change my name, I have to go through and cascade change every single one of those addresses. Because those kind of cascade updates and deletes are the real bane of a NoSQL system that has to handle multiple sets of data and make sure that they're all consistent. So here is examples. Data consistency. Read and write scale with a relational system. With data consistency, how can I add multiple different nodes and make sure that the data is all consistent in a relational system? With a NoSQL, as we described, it's okay if it's not. But with a relational system, you have to. Similarly, with read and write scale, typically with the MySQL, you have a single master that does writes. As soon as you add multiple masters, again, you have data consistency. Throughput and latency. As soon as you add multiple nodes and you connect them to each other, how do I make sure each of the nodes are participants in the transaction without slowing down the entire transaction tremendously? Application impact. If the database itself can't guarantee guarantees and consistency across every single transaction, I have to offload that to the application layer. And if I offload that to the application layer, I'm doing a lot of work in-house to make sure the database does things it should have been doing itself. Acid properties as we described. And so here's our first example of a MySQL scaling option that most people will automatically use, especially on the cloud, because you can go, if you're using a relational database service like Amazon has, you can deploy a new compute engine straightforwardly. I say if I have a 4XL, which has 16 cores, and I say I want an 8XL with 32 cores, I can point and click, and it can go from one to the other. The deal, though, is when you have a system like that, is you're limited by the size of how many cores are available. And also, since it's what is called vCPU, it's not a true core, so you're getting a hyperthread. And so even though it says 8 vCPU or 16 vCPU, or right now on Amazon RDS for MySQL, you have a 10XL, so it's a 40 vCPU. If you get 20 of those are physical cores, you're lucky, but oftentimes you don't. So what will happen is you're not actually getting the capacity you want, even though they say they have a very large number of vCPU. What happens if the largest vCPU they allow you to provision is not sufficient for your workload? You hit capacity limit. Most clouds provide up to 64 vCPUs at most for a single server. There is, for example, the X1s on Amazon, and now you're no longer in their RDS layer. You're going to be in the regular EC2. And that means that the point and click changing from one node to the other is not going to happen. And you're back to the regular problem with what we call scale up, is that you're going to have to take one system, it's taking all your transactions, you bring up a new larger system, you pick a consistent backup from the first, you bring it up on the second, then you set up replication on the second, and you wait until it catches up, and you do a failover. As you can expect, this is kind of a pain. And going back down is really not trivial. So being able to add capacity and remove capacity on demand, that example I gave, when you have, for example, a peak workload, not just on e-commerce, for example, in a gaming company when they do a new release, or any kind of application SaaS provider which has a new release or a new, all of a sudden, cascade of customers. These kind of things are a problem when you have scale up. But scale up is kind of good if, without any application changes that's needed, you can handle your workload in the particular environment they provide. If you can simply click and add a new node, and the node itself is larger, and it happens very trivially, and your workload isn't going to expand past that, you're fine. So this is not a bad problem if you're a smaller workload. Read slaves. Now, when people talk about capacity, they often say, well, I can always add more capacity. And what they really mean is they're adding read slaves. For example, Amazon Aurora says, oh, we can, of course, we scale. We add 15 read replicas. And this is true. They can add 15 read compute nodes to point at the same shared storage layer. But what that means is all the writes are still going to a single master. And what that means is when that write master is over capacity, that's as far as you go. So with the positives here, it's very simple to implement. There's lots of automation available to add read slaves to your system. The read-write fan-out can be done at the proxy level. You don't have to make application changes if you want to just do a brute force, any read transactions go to read slaves. The flip side of this is, of course, it's best for read-heavy workloads. It's also the data consistency can have an issue. When you have read slaves, there's going to be some level of seconds behind master. Now, if you have a regular topology and you have two different nodes, a write master and a write reader, and a read slave, or multiple read slaves, the system will be sharing the data back and forth across the wire. If you have a shared storage system like RDS at Amazon, each of the different nodes are actually just compute nodes pointing at the same shared storage. There's still going to be latency there, even though the data isn't being moved across the wire, because you have to release the write lock. And what will happen is, in many systems, for example, in e-commerce, for example, Magento, which works on MySQL, when you set it up correctly, it knows don't ever check a read slave in the checkout cart process. For example, if I go to the checkout, I add something to my cart, and I press I want to buy it. If it checks the available to promise at that moment from the read slave, and that moment in the read slave is a little bit behind the master, you might have just allowed yourself to do a transaction where the available to promise didn't match the inventory. And that's a problem. So, and that means the most valued transaction in the system, which is obviously the checkout process, actually shouldn't leverage the read slave. So it means that for the transactions you don't care about can go off the read slaves, and those are things like, people are looking up things in the catalog, people are checking this and that and the other. Oftentimes those are already offloaded to your CDN, your content data network. So the read slaves aren't providing you nearly the information and the capacity you need when you actually do things that provide money, the high value, high volume transactions. And what that'll also mean, for example, is for systems that you don't even expect that are going to be high volume, high value transactions. Here's an example of Pinterest. Pinterest has a multiple node sharding topology. Each of the nodes is master-master, and they don't use read slaves. They use master-master for high availability. No read slaves because they do not want to have the problem of that read consistency. And they're sharing pins, and they're sharing cards between users, and you wouldn't think of that as a high volume, high value transactions, but they do. Now we go to master-master. Now the classic implementation of this is just two simple nodes. Each of the nodes can provide any of the writes, any of the reads, and the two are completely synchronous. And as our lead sales engineer likes to say, if this worked great, we'd never stop, go past here. This would be wonderful. The problem with this is it's not nearly as easy as you might think. It adds reads and write scalings without needing to shard. And depending on the workload, scaling can approach linear. Now, I mentioned it's the classic master-master topology is just two nodes. Sometimes you can add three, and it gets really tricky. Another way of providing master-master is to do something like the Galera protocol. So, for example, MariaDB with Galera Cluster or Percona ExtraDB. And so what that does is does a master-master topology across multiple nodes using write sets. And so when I do a transaction on one node, it sends the write set to the other nodes. They confirm that they can run them, and if so, they send an ACK back to the master. So they actually haven't completed the transaction in each of the other nodes, and so the master that started the transaction says, yes, I'm done. And what that'll mean is you can get faster replications. So part of the synchronizing between different nodes is optimized. But the flip side, what this means is it's much better optimized for a highly available system and much worse optimized for multiple writes. So for example, if I want to do a write on multiple masters simultaneously with a single transaction, very similar to the Oracle rack problem, it doesn't do this very well. And if you actually look up the CoderShip libraries front page, they say, yes, this is great for write scale and a consolidation workload, but we don't recommend taking high volume writes on multiple nodes simultaneously. So this is a problem for write scale. There's another problem over here, is application changes are required to make sure that there is actual consistency and conflict resolution between the system. Now, some of the master-master topology systems like Galera and CoderShip can provide some level, and NeoDB does this, provide some level of conflict resolution, but really it's just a timestamp. Whoever gets in first gets it. And that's not the conflict resolution you want either. So to have intelligent conflict resolution, the database can't provide this for you anymore. So again, you have to push intelligence making into the application stack. And your application designers and developers want to actually do your business rules. They don't want to be doing plumbing. Here's two of the examples of how you can shard a system. These are the classic ways when people think of MySQL scaling. These are the ones they go to almost immediately. Now, vertical sharding is used in something like Magento. And what that means is, instead of breaking each table into separate chunks and putting them on separate servers, a vertical sharding is I can have a separate table on separate servers. And so, for example, I can put all the checkouts over here on shard 1, or I can put all my catalog there on shard 2, and I can put all my admin updates on shard 3, and for example, like this. And this will work if you can separate the workloads. Again, it's similar to a consolidation workload. And make sure you have a really good replication pipe for any kind of updates that are being made on the catalog to match what's actually in the checkout. Because that is what happens here. There's a limit to how much you can vertically shard before you say, okay, I've gotten to what I've done is one single write master can handle all the different writes of these tables until it can't. Then I separate the tables out, and then each of those masters can handle the writes to the tables until it can't. And now vertical sharding is at its limit. You can add read-write scaling with a good vertical sharding topology. It's much less difficult than regular sharding because you don't have to worry about skew of the deployment of when you're doing an application write and you want to fan it out. You know that I can say this transaction goes to this table because it's over there. I don't have to worry about, oh, it's a range within this particular primary key and which of the nodes actually take that. I can say if it touches that table, it goes to that shard. The flip side, though, is you lose transactionality again because each of the nodes are not exactly consistent with each other. The relational database management system that runs each of the write masters, if you have a MySQL, does not exist across multiple write masters. Again, the relational database management system that provides referential integrity, maintaining the parent-child relationship between tables, maintaining ACID guarantees with the transaction. Nothing like that exists in a database that masters all the rest of the databases. It has to be written in an application layer or in a middleware. Another issue is consistent backups are very hard to manage. I was sitting in a very large enterprise room, and they were talking about they have typically 128 to 200 shards for their deployed systems. And I was talking to the DevOps lead, and he says, yeah, consistent backups, just forget it. If you want to bring back a shard, and you want that shard to be consistent with the other ones, they bring it back up, and they hope the database is close to a point in time, and then they go in there and match the transactions. And that's terrible. But that's what they have to do because they have to give up a lot to get that right scale. And then finally, data maintenance of the shards to maintain your hotness and your skew. What will happen is you try to deploy the system between different nodes, and you try to make sure that, okay, maybe if I do a range partitioning on the last name, A through K is over here, L through M is over there. Whichever sharding key you pick, at some point, the data load is going to migrate a little bit from your expectations, and now one node's got way more hits and way more data than the other ones do. Taking that data off and moving it to another node typically requires downtime of at least 1 to 2 shards. And that kind of thing creates not only unavailability to the actual end users, it actually creates more consistency issues. Here is regular horizontal sharding, which everybody is probably familiar with. What this means is you partition a table and you put it across a different system. Now, when we say different system, though, that's an important distinction. Each of those nodes that you've partitioned your table to is a completely separate RDBMS. And so if you have any transactions that stay local to that node, that RDBMS can guarantee ACID transactions. But if you have a transaction that goes across multiple nodes, there's nothing that can do that for you. And so that's, for example, a problem with Vitess, which is a scale-out middleware solution that they use on YouTube, that they use at multiple different sites that are trying to get huge amounts of scale, and then they run into the problem, oh, I needed a transaction that crossed multiple nodes. It's not supported. Now what do I do? So what you'll have is systems that try their hardest to architect around any cross-node transactions, which means either have to duplicate the data across multiple different nodes so each local shard can access, for example, the customer records, and now I'm back to seconds behind master problem with replication, or I try to avoid those transactions completely, and now I have lost business functionality. When a person goes to, for example, their cart, and then they say, okay, other people who bought this also bought that, and they can't do it, sites that do very well in e-commerce, for example, are able to say, oh, you have these 5 things in your cart. Well, other people like to buy that too. Well, you can do that separately with analytics. But what about people who have this in their cart also buy this, 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 and this, and they've bought this many in this last 10 minutes, so you probably want to buy it. That's the kind of thing which really has a response to the customer and really hard to do with a sharded system. So the problems with horizontal sharding are similar to the vertical sharding as we discussed, and they're even worse. So you're going to have your skew. You're going to have difficulty to provide ACID transactions. You're going to have data management, skew, and consistency backups problems. So to circle back for our questions for today, what measures tell you MySQL deployment is hitting capacity? Well, for example, your query latency is over 20 mils. When you get your query latency over 20 mils, you think, that's nothing, right? But a site, whether it's a customer-facing site or an internal site on an application, actually has way more than a single application database transaction. Oftentimes, with an AJAX call, you're cutting in multiple different database transactions, and even though they're in parallel, if you can, when they start adding up, you're starting to hit that 1 to 2 second limit. So if you have query latency over 20 mils, so for example, when Amazon showed that their benchmarks for Aurora, they showed 100,000 transactions per second, and they ran that against an 8XL, which is 32 vCPU, and they had 4 8XL drivers. To get 100,000 write transactions per second at 100% writes on Suspense, their latency was cranked up to 160 mils. So that's terrible. And not too many of those will now, if you use that as a model for an active e-commerce site, pretty soon this transaction is it's not working anymore. The system's so slow that people are just going to go somewhere else. Or similarly, your server is at 60 to 70% CPU sustained. You have no room for peaks there. If anybody else tries to enter that system or you get a surge of users, the entire system's going to slow. Your memory or network can be up to 80% capacity. Now again, that's not the CDN, that's not Memcache, that's specifically the MySQL write server itself being under capacity and overutilized when it comes to their memory. So too much memory per actual thread. And so you'll see that a lot of different systems that are trying to optimize MySQL are trying to do things like forcing the memory per thread to be lower, or actually aggressively kicking transactions that try to get too much, which is not so great. Destroying transactions in order to keep the system up is kind of robbing Peter to pay Paul. Similarly, modifying max connections no longer helps. Failed connections per hour keeps rising, even despite connection pooling. So these are some of the highlights that show you your MySQL system is going to start to need to look at some of these different options to scale. How far can you improve your MySQL capacity with hardware? So there's a quick overview of what we described. Read slaves, you're still limited by the write master. Scale up, you're limited by the instance max capacity. With master-master, you're limited write scale for homogeneous workloads. Again, if I have multiple different applications on the same cluster or grouped protocol for master-master, for example, Galera, that's okay. But if a single application needs to have more and more write, they don't recommend doing that. One write master only. Vertical sharding, you have limited transactional ACID across shards, and similar to horizontal sharding. So what is a different way of doing this? ClustrixDB itself is a system that provides the applications are able to connect to multiple nodes simultaneously. You're able to scale linearly with each node you add, and you can add those nodes or remove those nodes with a couple of clicks. You don't need to replicate, and you don't need a shard. You get more transactions, more connections, more writes, more reads from the system, and it's MySQL compliant. So the ideal way is to take a MySQL dump from your current MySQL system, bring it up on our system, and it'll actually bring it up faster because we have multiple parallel systems. All the data is going into multiple nodes simultaneously. And when you're done, you can just simply point your application to us and away it goes. Let me give a little bit more detail there. A write and read linear scale-out system. It's fault tolerant, it's MySQL compatible. It's ACID compliant across all the nodes with all transactions simultaneously. The best way to describe this is, to your application, it sees one MySQL instance. To your actual infra behind that, you have as many nodes as you want. We have 60 node deployments where people are running multiple nodes, 64 for example, and we'll show you a benchmark, where all those nodes are running simultaneously, the same workload, and any of the application asks, queries, or anything are fanned out across multiple nodes the data is kept in multiple places, and it comes back to the user, and the application does not know that it had to jump to multiple nodes to get those results at a very, very high speed and low latency. It handles transactions and joins transparently, completely relational system. It's optimized for OLTP. You're not going to add thousands of nodes like Hadoop, but on the other hand, you're not going to get the latency between the nodes like you get in Hadoop. Built-in fault tolerance, the system has multiple copies of the data for you. Flex up and flex down is our way of describing that you can add nodes on demand or remove nodes on demand. So that whole issue of when you have a peak access pattern, for example, Cyber Monday, you can add nodes for that. We have companies that work with us that go from 8 to 10 nodes before. They get up to 20 to 25, 30 nodes for the end of the year, and then they come back down afterwards. And minimal database administration, that's the best part of this. When you get right scale to a system, then you worry about, for example, consistent backups, you worry about hotness. We have multiple patented rebalancer that'll do those things for you. It's built to handle the cloud. We have deployments on Amazon, Google, Azure, Rackspace. It also runs very well in your own data center. And taking one step into this deeper, let's describe what actually happens under the hood. A typical deployment out of the box, standard, is a minimum of 3 nodes. Each of those 3 nodes are completely shared nothing. They're all ACID compliant at the transactional level. So the system supports transactions, joins. All nodes are equal. There's no leader, no follower. Any incoming transaction lands on whatever node is available, a very simple round robin from, for example, HA proxy or EL5. And from there, what will happen is the system generates a session. That session takes the SQL. The SQL is broken down to fundamental parts and sent directly to the node on which the data resides. It's run locally there, and only the return result set is sent back to the originator node. The originator node is the leader for that particular transaction. And what that means is you minimize the amount of data movement across the cluster, and you maximize the parallelism. All the servers accept client connections, and this is one of the first secret sauce, if you will, is the ability to fan out the query at the fundamental component level, if we call them functions. The second one is actually tables and secondary indices are distributed across all the nodes. That means, and I'll show you right here, oops, did not have the slide I expected. What that means is each of the nodes has a data map. And that data map tells you where all the data in the rest of the cluster resides. And the reason it can do that is we use 64-bit consistent hashing. And so long story short is any node that receives a query knows exactly where the result set it's looking for is. So you minimize the hops. So now the broadcasts are really minimized because I'm able to go directly to the node in which I know the data is going to reside. And so with that data map and with the ability to fan out the actual functional primitives of each query, and finally, with the automatic rebalancer. These are the 3 ways we're able to scale out our system. But again, this sounds great in theory. Let's show you a little bit of performance benchmarks that kind of put a little bit of proof to the pudding. So with a regular sysbench OLTP, and a 90-10 mix is a lot more realistic than 100% writes or 100% reads, because 100% writes means the system just takes writes, and by not taking any reads, you never have to hit contention. So for example, in the Aurora benchmark, when you do 100% writes, even though they got their up to 100,000 transactions per second, and their write latency was scaling up to 160 mils. If they add any reads to that, the reads would just absolutely go through the roof because in terms of latency, because you have to release the write lock in order to read. So here, let's get out of that problem and put it right on the screen. 9 reads, 1 write. What you'll see here is as soon as you add more nodes, you simply get more and more and more transactions against the system. And what we encourage you to do is consider 20 milliseconds as a good cutoff before you should just add more nodes. So you see, that's approximately where the knee is for us. So when you add more nodes, you just continually get linear scale. And if you say, hey, I don't like that the latency is starting to climb, then add more nodes. Here's the slide I like the best. We compared MySQL, their largest instance, which at the point was 32 at 8XL, 32 vCPU. We'll run it again on the 10XLs they have now. And Aurora's biggest instance, which still is 8XL. So 32 vCPU for MySQL, 32 vCPU for Aurora, and we had 4x8, so 4 2XLs. So we had 32 vCPU. And as you can see, we all kind of hit right around 20 milliseconds, right around 9,000 TPS at the 90-10 workload. But what happens there? When you start to add more transactions to Aurora, it just starts to go, the latency started to scale really high, similar to the Workbench, Sysbench benchmarks that they provided themselves. With us, you just simply add more nodes, and more and more and more. And you say, well, okay, well, in this case, you have 20 nodes. How far can you go? Well, here's an example, because we were chasing some numbers. Here's 64 servers running 2.2 million queries per second using Sysbench 100% reads. So we can do what we're talking about. Let's give you a little bit more detail of how that actually works. Here's the slide I was mentioning before. Each of the nodes is going to have its own query compiler, its own data map, its own database engine, and its actual data. And so what that means is each of them shared nothing. That means each of them I can just remove one. If I have 3 nodes, I can remove one, and the system still can run, but it's going to scream and say, please add another, so I can be fully reprotected. If I remove 2 nodes from a 3-node system, if you're familiar with Paxos, it's called, now you don't have enough for quorum membership. If I have 4 nodes and I remove 2, that's called split brain. So the system itself is using Paxos, and it knows I need to have half plus 1 in order for the system to work, or plus partial. So for example, 5, I can lose 2 because I have 3. And what that means is you have a partition event, and if there's 5 nodes originally, and all the nodes know there's 5, that's your static membership list, and there's a partition event, and 2 of the nodes can't see the other 3, those 2 nodes know, hey, I can do the math. 5 divided by 2 plus 1 is more than I have, so I can't come back up as a cluster. The other 3, if they can see each other, say, I have 3. Now the deal is, since each of the nodes has 2 copies, not all the data on each of the nodes, but the entire system has 2 full copies of the data, what we call replicas. That means that even if I've lost 2 nodes, I'm going to have a full set of copy on the 3. And interestingly enough, if I set what we call N resilience, and I have, for example, 20 nodes, and I say, hey, I want to lose 18 of those, that means I can set the system to be completely redundant to 18 copies of that data. And so what that means is I can make that system as fully redundant as possible just by clicking a couple of knobs in our system, which is actually unprecedented. Typically, when you have something like this, N resiliency, or it can be called other things, you get 2 nodes, sometimes 3. But we can have, you can change the knob as much as high as you want. Intelligent data distribution, what that means is the first part is sharding, when you described, with a different way of scaling out a system is you have to pick a partition key, you have to tell your application how to track that, you have to track the data migration, you have to make sure the data goes where you need it to go, and you make sure your application queries go there too. We don't do that at all. The system behind and underneath the hood will automatically, when you create a table, automatically do what we call as a slice and distribute that data for you across all the nodes. So for example, when you create a table, this case it's going to be 5 slices for these 3 nodes and a replica for each of those slices. So there's 2 copies, a primary and a secondary. And so the primaries are distributed and the secondaries are distributed. And so what that means is if you lose that node, you still have 2 copies, and the system says, oh, I have a primary still, I don't have a secondary, I'll automatically rebuild it. Similarly, when you want to flex, when you want to scale out or scale in, I can click and I add a node, and the system will say, oh, okay, I can move some of the data to that node and automatically rebalance for hotspots. The similar case happens when I want to scale back in, and I say, oh, I actually have too many nodes now for my seasonal peak. What I can do is tell the system what we call a soft fail, and say, take that node, make sure that there is redundant copies on the rest of the remaining nodes, and when you're ready, that node is ready to remove from the cluster. Flip side is, if you're on the cloud, for example, and a cloud event happens, and an instance goes away, or a multiple instance goes away, if that multiple instances have gone away that is lower than your N resiliency setting, so for example, if you lose 2 nodes, then the rest of the system knows it has to rebuild itself because it has the copy, either the primary or the secondary replica is lost, but you don't lose both. And from there, you're able to rebuild the system automatically because the system is automatically checking, and we call that the rebalancer. The rebalancer automatically creates table slices across all the nodes on initial data. Data growth, it automatically says, okay, that slice got too big, let me split it and redistribute the smaller slices. Flex up and flex down, as I just described, it automatically knows how to soft fail or add a node or remove a node. Failed nodes knows how to reprotect. If I don't have my primary and my secondary replica, or I can change the knob and I say I want to have 3 replicas. If I don't have all 3, the system will automatically know to add additional redundancy. New data means if I have too much hotness on a single node, if I have too many access points, even though the data isn't that big, I know I still need to split that slice and move it somewhere else. So not just splitting on when there's too much data there, splitting when there's too many accesses there. And we have multiple patents on that guy. That is about wraps it up into a little bit of overview of our solution for things. Does anybody have any questions? Okay, one of the things coming over is, and it's an example that we get again and again, isn't this just like sharding? So a little bit of an overview again. This system allows your application to think it's talking to one MySQL. Whereas with sharding, you're talking to a system that has to automatically distribute queries across multiple separate RDBMSs. Now you have sharded middleware that knows how to distribute those queries, but many of them, for example, Vitesse, cannot handle cross-node transactions, which means if I have the inventory scattered across these tables and I have the actual customers scattered across those tables, and I want to do something like, I want to compare customers to the inventory actually being used and then to the available to promise, if I've got to do that across multiple nodes, that system can't handle the transaction, whereas our system does transparently. And so sharding itself allows, if you have a particular workload that does not require cross-node transactions, so for example, some reports run really well because you can have redundant data across multiple nodes. And so flip side, with a sharded system, you're going to have redundant hardware all over the place because in order to get redundancy, each node has to have its own separate copy of itself. So if you have 10 nodes, you're going to need at least 20 to have redundancy. Whereas with here, 3 nodes have 2 copies of the data. And so what that means is you've actually provisioned less hardware to get the redundancy you're looking for, and you don't have to follow up and make sure your application is smart enough to do the things the database should be doing for you, the relational database management system. I was talking to a senior vice president of IT at a very large bank, and she said at some point maintaining their sharded arrays, they had 228 arrays of shards, for one of them for a reporting system for their CEO, and the other one for an application system that was very OLTP. And she found that at a certain point, she was no longer just maintaining the hardware. She had to build her own de facto development group in just her IT group, which she kind of had to shelter from the actual CEO, because every time they say, oh, we want to do this with a report. See, a sharded topology harkens back to the old days where you built your data store to match your query set. And that's fine until they say, oh, can I have a new query? And all of a sudden your data store doesn't match that query. And now you're going to have to start modifying things to make sure that new functionality can be handled by the old data store. And this is exactly the problem that relational databases are designed to solve. Ad hoc queries, change the business rules on the fly. That is what you can do with a relational system, and what you can't do as soon as you start taking away some of this relationality. I'm available at @InSomelyDave. I'm also available at Clustrix if you wanted to have any questions to follow up on our material today. But otherwise, thank you so much for attending.